Let's look at the chemical equation on the screen. This is the process where SO2 and O2 combine to form SO3. The most important part here is the numbers in front of the molecules, which represent the reaction ratio. The equation shows that 1O2 is needed for every 2 SO2 molecules. In our current situation, we have 4 SO2 and 4 O2 molecules ready. Based on the 2:1 ratio, to completely react all 4 SO2 molecules, we only need exactly half that amount of O2, which is 2. Now let's see how many SO3 molecules are produced. The equation shows the ratio of input SO2 to output SO3 is 2:2, meaning they are exactly the same. Therefore, since 4 SO2 molecules reacted, the final number of SO3 molecules produced will also be 4. Now, let's calculate the moles using the ICE table. Before we dive into the calculation, let's clarify exactly what the letters I, C, and E stand for. I stands for initial, meaning the starting state. C stands for change. And while E normally stands for equilibrium, in a reaction like this that goes 100% to completion until a reactant runs out, it's much easier to think of E as end, the final state. So, let's solve this assuming we initially put in 5 moles of SO2 and 2 moles of O2. First, the I, initial step. Since the reaction hasn't started yet, we write 5 under SO2 and 2 under O2. The product, SO3, hasn't been formed yet, so it will be 0. Now for the key part, the C, change step. We need to run the reaction all the way until one of the reactants reaches 0. Which one will hit 0 first? Looking at the chemical equation, SO2 and O2 react in a 2:1 ratio. If we assume we use up all 2 moles of O2, because of the 2:1 ratio, we would need 4 moles of SO2. Since we have 5 moles of SO2, we can use 4 moles and still have some left over. Therefore, the limiting reactant that runs out first and becomes 0 is O2. Then let's write down these changes. O2 uses all 2 moles, so it's -2. Here, because the coefficient of SO2 is twice as large, the amount of change must also be twice as much. Therefore, SO2 uses 4 moles, so it's -4, and the produced SO3 will be +4. Finally, the E, end step. This is really simple. You just add the I and C together. SO2 started with 5, and we use 4, so 1 mole is left. O2 started with 2, and we used all 2, so it becomes exactly 0. As intended, one of our reactants has reached 0, and we can see that 4 moles of the product, SO3, are finally produced. By drawing the IC end table like this and making one of the reactants 0, the calculation becomes very intuitive to solve. Looking at the initial state in the I row, we have 5 moles of sulfur dioxide and 2 moles of oxygen. The product, sulfur trioxide, starts at 0 moles. In a true chemical equilibrium, it is impossible for any reactant to completely disappear and reach 0. Since all reactants and products must coexist, we cannot determine how far the reaction has progressed without knowing the final state. This is why problems typically provide the amount of product formed as a starting point. Let's assume that 0.5 moles of sulfur trioxide were produced at equilibrium. In the C row, this means sulfur trioxide increases by 0.5. Based on the stoichiometric ratio of 2:1:2, oxygen must decrease by half that amount, which is 0.25 moles. Sulfur dioxide decreases by the same amount as the product, which is 0.5 moles. Now we can determine the final amounts for the E row. We have 4.5 moles of sulfur dioxide, 1.75 moles of oxygen, and 0.5 moles of sulfur trioxide. By using the known amount of one substance, we can successfully calculate the equilibrium concentrations for every component in the reaction.